Welcome back to The Explainer. Today, we are getting into the weeds with a real masterclass on enterprise network architecture. We're going to examine the exact blueprints and the actual Terraform code for building a production-grade AWS multi-VPC hub-and-spoke environment. Honestly, if you've ever needed to strictly segment environments while keeping your security and logging completely centralized, this is exactly how it's done. Okay, let's dive right into this. Here's our roadmap for today. We have 6 major sections to cover in this order. We'll start with Section 1, Project Overview and Architecture. Then, Section 2, Terraform State Locking. Section 3, Hub VPC and our modular approach. Section 4 covers Spoke VPCs and TDW attachments. Section 5 is all about TDG routing and centralized egress. And finally, Section 6, the EC2 module compute layer. All right, kicking things off with Step 1, Project Overview and Architecture. So check this out. What's really fascinating about this level of scale and segmentation is how the traffic is actively managed. Instead of having every single environment manage its own internet access, which is a nightmare, one central hub VPC, right up there on the top left, at 10.0.0.0/16, owns all the shared infrastructure. That includes the internet gateway and the NAT gateway. Connected to it via that central transit gateway are our spoke VPCs. We have a dev VPC, a prod VPC, and a shared services VPC. We're enforcing strict environment isolation right at the network layer, which means dev and prod literally cannot communicate directly. Plus, we're operating on a strict least privilege model. There are absolutely no public IPs for workloads, zero SSH access, and no bastion hosts anywhere in this entire design. To quickly recap Step 1, we've got a hub that centralizes all internet egress, spoke networks for dev and prod that are strictly isolated from one another, and a heavy least privilege approach where traditional SSH and public IPs are completely ripped out. Moving right along to Step 2, Terraform State Locking. To guarantee safety across deployments, let's look at the Terraform block where we specify the S3 backend. First, we point the bucket to Sunil P2 TF state to safely store our versioned remote state. Next, we define the exact file path key for the HubSpoke state file. We set the region to AP Southeast 2, and then explicitly set encrypt equals true to enforce security at rest. Finally, here is the absolute most crucial parameter, the DynamoDB table set to Terraform lock. This table uses atomic conditional rights to act as a lock flag, meaning if 2 CI/CD jobs run at the exact same millisecond, DynamoDB ensures only one gets the lock, completely eliminating race conditions. Recapping Step 2 really quickly. State locking is your ultimate safety net. Combining S3 for reliable version storage with DynamoDB's atomic rights ensures safe, exclusive state updates across your whole engineering team. Next up is Step 3, the Hub VPC and our modular approach. Let's walk through this. We start by defining module Hub VPC, sourcing it locally from ./module/VPC. We set the VPC name to Hub, assign it a massive 10.0.0.0/16 CIDR block, and carve out a public CIDR of 10.0.1.0/24. But pay close attention to this final flag. Create IGW equals true. Inside our module, this single Boolean condition is what actually creates the public subnet, the internet gateway, and the public route table. It ensures these public resources are only ever created for the hub, which keeps this exact same module entirely reusable for all our private spokes. So, our Step 3 recap. A single custom module creates literally every VPC in this architecture, but only the hub is granted public-facing resources, all controlled elegantly by that specific create IGW Boolean flag. All right, that brings us to Step 4, Spoke VPCs and TGW attachments. For the attachments, we define an AWS EC2 Transit Gateway VPC attachment resource, and we'll name it dev. We lock this into our central transit gateway by passing in the transit gateway ID and then dynamically pull in the VPC ID using var.dev VPC ID exported from our earlier module. By specifying the subnet IDs as var.dev private subnet ID, we anchor this attachment exactly where it belongs in the network. Finally, we apply our tags, naming it dev TGW attachment. It's important to note that the root module passes these IDs into the TGW module only after the VPCs are fully built out. Recapping Step 4, Spoke VPCs are strictly private because they use create IGW equals false, and they hook into the main architecture via these dedicated transit gateway attachments, which sequentially depend on the VPCs being created first. This brings us to Step 5, TGW routing and centralized egress. This is where the magic really happens. First things first, we absolutely must disable AWS's default behavior, which otherwise just allows all VPCs to blindly talk to each other. We create the Transit Gateway resource, give it a description, and explicitly set default route table association to disable and default route table propagation to disable, followed by tagging it. Now, because we shut off those defaults, we have to build custom route tables. We define an AWS EC2 Transit Gateway route table for the hub, tie it to the Transit Gateway ID, and tag it RT Hub. We then duplicate this exact same blocking configuration to create tables for dev, prod, and shared. With our custom tables built, we must define the propagations. Basically, who is allowed to see whom. We declare an AWS EC2 Transit Gateway route table propagation named dev to hub RT. We provide the attachment ID for dev and inject it into the route table ID for the hub. We do the exact same thing for prod to hub and shared to hub. But look closely at the RT dev section down below. We propagate hub to dev and shared to dev. Notice what's missing? There is absolutely no propagation between dev and prod. By simply omitting that single block of code, dev and prod CIDRs are explicitly not propagated into each other's route tables, achieving rock-solid isolation by omission. This diagram brilliantly illustrates the resulting logic. Look at step 2 here. We have our attachments. In step 3, our custom route tables. In step 4, we explicitly associate one to the other. And in step 5, down at the bottom, you can see the exact propagations we just coded. Notice the red X's? The dev attachment is explicitly skipped in the prod route table, and the prod attachment is skipped in the dev route table. This is true network isolation implemented purely at the routing layer. Let's actually trace a packet's journey for centralized egress end-to-end here. Follow the numbers with me. Step 1. A dev EC2 instance tries to reach the internet. Step 2. The dev private route table has a manual default route pushing 0.0.0.0/0 to the TGW. Step 3. The packet hits the TGW dev attachment. Step 4. The TGW RT dev doesn't have a specific propagated route for the internet, so it falls through to a manual static default route pointing directly to the hub attachment. Steps 5 and 6. The packet lands in the hub's private subnet. Step 7. The hub's private route table has a manual default route sending traffic straight to the NAT gateway. Step 8. The NAT gateway translates the IP. Step 9. The hub public route table sends it to the internet gateway. Step 10. The packet reaches the internet. And the return path follows the exact reverse, utilizing those TGW propagations we just set up. To recap, step 5, TGW defaults are turned entirely off. Our specific propagations deliberately isolate dev and prod from each other. And all external internet traffic is securely forced out through the hub's centralized egress via static default routes. Finally, we reach step 6, the EC2 module compute layer. For our compute security, we create an IAM role named EC2 SSM. The assume role policy restricts the action to STS, assume role, and the effect to allow, setting the principle so that only the ec2.amazon.com service can actually assume it. Then, looking at the security group named EC2, we specify the VPC ID and define an egress block allowing traffic from and to port 80 over TCP, plus a second egress block for port 443. Now, notice what's missing here. There is absolutely zero ingress block. The security group has no inbound rules whatsoever. It relies entirely on outbound connections for systems management. Moving to the EC2 instance resource itself, we declare the AWS instance. We define the exact AMI and set the instance type as T3 micro. We map it to the subnet ID using our private subnet variable. We associate our IAM profile by referencing the IAM_instance profile MAME and attach the security group using VPC security group IDs. Then, vitally, we explicitly set associate_public IP address to false. We enforce IMDS v2 by setting HTTP tokens to optional in the metadata options. And finally, we inject a boot script into the user data to securely bootstrap our Flask application. To bring it all together, the root module actually calls the EC2 module for the dev environment. We set the source path to our local EC2 module, pass in the environment variable, and then we inject the required outputs from our VPC module, specifically the private subnet ID and the VPC ID, to ensure those compute resources are placed precisely in the isolated network we just designed. Recap for step 6. Our workloads are completely private, with absolutely zero inbound ports open. Access is handled entirely via outbound SSM session manager connections. I'll leave you with this final provocative thought. If you can architect and manage a massive enterprise fleet entirely without SSH keys, bastion hosts, or public IPs, what other legacy security assumptions should we be questioning today? Thanks for joining me on this explainer. See you next time.